Hi there and welcome to the course. I've added this video in right at the very beginning because over the last year I've had a few people who haven't done any electronics whatsoever and they don't know anything about basic electronics or gates and they're starting from absolute scratch, and I never had a video that actually described some electronics and what gates are and how they work and why we use them. So I've added this video in at the beginning in order to go through this. So if you already know this stuff, you can always skip over this video and go into the second video in the course. If not, then it's well worthwhile sitting down and have a little listen to what's happening over this next 10 minutes. So we're not going to become experts on electronics over the next 10 minutes. It's just a light introduction just to get you started if you don't know anything about electronics or computers and you're starting from absolutely from scratch. So we know that a computer works using electricity. Now we know that because we plug the computer into the wall and it goes, but a computer doesn't necessarily need to be built so that it runs on electricity. You could build a computer that would be pneumatic, that would run on air. You could build a computer that's hydraulic, that would run on oil. And in the first computers that were ever built back in the late 1800s were actually built from gear wheels, so it's cogs and wheels. But we're going to start off with the assumption that we're not using a computer that's made up of cogs and wheels. Our computer is going to be electrical, or as we say, it's going to be electronic. Now what we're going to do is we're going to use devices. Now we won't get any details on what these devices are, we'll just show you them just to get started. But what we want to be able to do is we want the device to switch really quickly. I mean, what do we mean by switching? Well, to change from one value to another value really fast. And how fast I mean by really fast? Well, your computers that you've got nowadays, they can run at speeds of maybe up to 5 gigahertz. So that's 5,000 million switches that it can do every second. Okay, so that's a huge amount of switching, meaning it switches really fast, super fast, and that's what makes computers really useful. So what do we mean by switching? Well, a computer goes from a low level, so I've got the low level represented here, to a high level, and that's your high level here. Now, the low level, if we like here, to make it simple, we could say that's a value of 0 volts. Now, we don't need to understand about volts and currents. We just need to know that there's something here called a volt and it sits at a 0 volts, and this is the low level. Now the other level is the high level and it's a value of 5 volts, and we can switch between 0 volts up to 5 volts super fast, and we can go from 5 volts down to 0 volts super fast. So this is the switching that I'm talking about. So the 0 volts, we'll call it sometimes here called a low, or we'll call it a 0, and the 5 volts we'll call it a high or a 1. Now the reason why we're going to start using the value of 1 and a 0 is that we can now go ahead and we can start implementing something called some Boolean logic, and Boolean logic allows us to build up really fascinating useful circuits, and that's what we're going to be doing over the rest of the course. So we know that 1 is a high or a 5 volts and a 0 is a low or a 0 volts. But what is this device that switches? Well, the device that switches is a device called a transistor. And this here is a mock-up of the very first transistor that was created, and this one is around about 1949, I believe. Now we don't need to know how this works, we just have to have a little look at it just to see that there is such a thing as the very first transistor, and this is what it looks like. And we're going to be using this transistor as a switch, meaning this is a device that can turn on and turn off super fast. So of course this transistor in this form here isn't of much use to us, but over the years they developed processes to take the transistor and make them a little bit smaller. So this is another transistor here, and this is like the size of your smaller than your thumb, so just the end of your thumb. It's maybe about maybe a centimeter or 2 centimeters long. But this still isn't very good. It's still, for us, if we're wanting to do any design that involves thousands of these, or actually hundreds of millions of them now that you get in a modern CPU. So before we leave this page, I'm just going to show you the symbol here, and this is a symbol for something called a bipolar transistor, and it just represents this transistor here. So let's move on and we'll see how we're able to take this simple transistor and we're able to squeeze them into an integrated circuit, which is taking hundreds of millions of these transistors and sticking it in a piece of silicon. So the engineers took that simple transistor, which we've seen in the previous page, and were able to pack a lot more of them into this thing here called an integrated circuit. So basically this is just almost like a block of brick, so it's almost like a block of cement. There's very little can go wrong with it. Now we don't need to know all the details of what's inside that would be a whole different course, but we just need to know that we're able to take maybe a few dozen of the transistors we've seen in the previous page and pack them into one of these. But of course over the years these chips have got smaller and smaller, or in fact the number of transistors that we can squeeze into one of these chips has got bigger and bigger. So if you had a chip like this, it might take a few dozen or a few hundred transistors, and we move over to a modern CPU. So here's an Intel Core i9, and this will contain hundreds of millions of these transistors. So imagine you had a piece of equipment, a piece of machinery, which one has got hundreds of millions of these transistors, and the transistors can switch at 5.3 billion times a second. And then you could imagine what we're going to be able to do with a machine that does that. And we're in a very, very privileged position at the moment in time, because we are the first lot of human beings that really understands what it means to have a machine that can do these things. And we've got them sitting in our front rooms, and you're probably sitting using one right at this very moment in time. So if you haven't done any electronics before, you're probably still scratching your head thinking, well, okay, but what is it that's switching, and why does it have to switch, and why is it that when things switch really quickly we can actually do something useful with them? You might be sitting thinking, say for example, I could switch on and off my light bulb in my front room 5 million times in a second, but it's not much use to me, is it? So what we have to do is we have to build up elements that are actually going to do some useful things. And the elements we're going to build up are things called gates. And that's just a generic name given to a simple element that will do some simple logic for us. So let's look at one of the most standard ones, our simplest one, and that's called the AND gate. So here's an explanation of what an AND gate is. Now we can build up this AND gate using two of these transistors. So these are just the transistors we've seen in the previous page, and it's a schematic diagram for one of them, and there's a schematic diagram for the other, so TR1 and TR2. Now you don't need to bother about these things, these are called resistors, and I've just added them in and we'll leave them in here for the moment. But we're trying to work out what's happening here with this little circuit. So this, if you haven't seen any electronic circuit before, will maybe be a bit strange to you, and we don't need to understand all of it. All we need to know here is that we've got an input A, so this is the input A, and we've got another input B. Now what do I mean by an input? Well, what I mean is that we have a point here that we control, and the voltage at this point can go high, or the voltage at this point can go low. The voltage at this point can go high, or the voltage at this point can go low, and we can control it. We decide when it goes high, and we decide when it goes low. Now the way that these transistors work is, you can think about it very simply as, imagine you had just a big bucket of water, and that's a bucket of water sitting here, and you had a pipe coming down. Then whenever it hits this point here, this transistor, it just looks like a switch. So there's a switch there. But by a switch, what I mean is, in this case, that's a pipe coming down, And if you think about the pipe, you could think about the pipe as being cut off at this point. So maybe you've got a little valve there that stops the water flowing down. So in effect, this is really like a little valve, but in effect, that's actually an electronic switch. Now we can come down here as well, and we can have this transistor here. Again, it just looks like a little switch. So there's no water going to flow down through this pipe because it's open here, and all the water just sticks at this point. So that means if you were to say measure the pressure in the water here, then the pressure of the water here is going to be high, and there's not going to be any water in here at all, so the pressure of the water is going to be low. So what we do is we'll actually say that although the pressure here is high, we'll actually say that if the pressure is high, we'll call that a 0. Now that might seem strange to you, but there's nothing wrong with it. Rather than using the word pressure high, we could just say, well, that is a 0. So we've just defined it as that way. So now what happens here is whenever we get a high input in here, and this is just the way this device works, if we get a high input in here, what happens is this closes over. Okay, so the switch closes. So whenever the switch closes, the water pours down to this point here, but the pressure in the water is still the same all the way down the pipe, and it's sitting at a value of 0, so it's still a high pressure. But let's say now we had this point here going high as well, so now this point is going high and this point is going high. So if this point goes high, what happens is it now switches this transistor, so that switch comes in here. So now the pipe is all joined together, so all of the water here can now flow down through the pipe. Now whenever the water is allowed to flow down through the pipe, it will flow down and it can just flow away, and imagine just flowing away into the blackness here. Okay, so the water just flows down and flows away. Now whenever the water is able to flow all the way down, it's freely able to flow. It means that the pressure at this point here will just drop. Now whenever we say the pressure dropped, what we're going to say is that with this point here is now gone to a high. So that's actually this point here. So high pressure will give us a value of 0, and the low pressure will give us a value of 1. So all I'm really trying to do here is make the electronic circuit look analogous to a mechanical system. So what we're able to do then is create something called a little truth table, and this is our truth table here for our AND gate. And let's work through this truth table. What we are saying is we've got 4 different inputs that we can put in. We can have the A and the B as low. We can have the A is low and the B is high. We can have the A is high and the B is low, or we can have them both high. And in each of these cases, we're going to get a different output here at this output. So let's work through each of them. We know that whenever there's a 0 and a 0 here, both these switches are open. So if both the switches are open, it means that there's a high pressure sitting here, so the output here, as we said, a high pressure is going to give us a value of 0. So a 0 and a 0 will give us a 0. So let's say we make one of these switches high. So if this one goes high, it means that we've closed this switch, but that switch still remains open, so there's no water can pass through. So that means that's still sitting at high pressure, so it's a value of 0. So it means whenever we have a 0 at A and a 1 at B, we've still got a 0 at the output. So let's now make the value of B high and the value of A low. So if A is low, it means that this switch opens up and this switch closes. So if the switch is opened up, again there's still going to be a high pressure here, which is a value of 0. So 1 and a 0 will give us a 0. But let's say finally we've got a 1 and a 1 in both of these. It means that both these switches are going to close. When both the switches close, all the water is going to be allowed to flow down through the pipe and out the bottom. So it means that the pressure here changes from a high pressure to a low pressure. And we've said a low pressure is going to be represented by a value of 1. So we can say that whenever you have a 1 and a 1 in here, we're going to have a 1 coming out. So this thing here is called a truth table. Now it's called a table obviously because it's a table, And it's called a truth table because it tells the truth. It tells you exactly what happens between the inputs and the outputs of this little circuit. So that's a very basic description, and I've tried to describe it in a mechanical way as opposed to an electrical way. And it doesn't matter too much if you don't fully understand that. What matters is that you get a grasp of a thing called a truth table. And this is a logic element, and it produces a simple logic. And this logic is called an AND logic. So this is an AND gate. And you can work this through actually just using English, because you can say, if A is low and B is low, we get a low output. If A is low and B is high, we get a low output. If A is high and B is low, we get a low output. If A is high and B is high, we get a high output. So this is our little truth table. So if you're really inquisitive, you're probably still sitting there scratching your head a little bit, because you can say, well, okay, I can understand that you've made a little logic element out of these transistors, but so what? How does a little logic element that switches really fast how is that of any use to us? Well, this is not the only logic element that we can make. We can use lots of different connections here of several 2, 3, 4 or 5 transistors, and we can make other sets of logic elements. Now, the really interesting part here is that we can join the logic elements together, and if we join the logic elements together, we can create vastly complicated structures. That is, we can create entire CPUs with hundreds of millions of transistors that do incredibly complicated things, and it's an incredibly complicated bit of circuitry. But at its very heart is the simple Boolean logic that you see here. And this is the Boolean logic for an AND gate. So let's have a wee look at some other logic gates. So just as the transistor has a little symbol associated with it, we actually create a little symbol for the AND gate. So every time we see an AND gate, we didn't want to keep drawing out those transistors all connected together. We just wanted some simple way of representing it. And this is a simple way of representing it here. We've got two inputs, which were our inputs are A and our B, and we've got one output. And we've seen the truth table for the AND gate already, and it tells us if both inputs are low, we get a low output. If either of the inputs are high, then we get a low output, and we only get a high output when both the A input and the B input are high, and that's our AND gate. Now we can join together those transistors in a different format, and we can create this thing here. Now this is another logic element called an OR gate, and the OR gate has got a different truth table. So in this truth table, we can see that we get a high output if either A goes high, or B goes high, or they both go high. So that's why we call it an OR gate, because we get a high output if either A goes high or B goes high, but we get a low output if both of them are lows, and we see the truth table for that here. So let's look at another two logic elements. So don't get too worried, there's only 5 or 6 of these elements that we need to look at, and we'll see the rest of them over the next couple of pages. We have the exclusive OR gate, and this is the truth table for the exclusive OR gate, and we see we only get a high output when either B goes high or A goes high. Now this other one here is an interesting one. It's called the NOT gate, and it's sometimes called an inverter. If we have a 0 at the input, we get a 1 at the output. If we have a 1 at the input, we get a 0 at the output. So this inverts the signal from the input to the output. We have something here called a NAND gate, and it sounds very much like the AND gate. And you can see this little circle in the front here. Well, this means that the gate has actually been inverted. So this thing here, it actually just looks like the normal AND gate which we've seen on the other page with a NOT gate in front of it. And this is the truth table for the NAND gate here. And we can also do the same thing with the OR gate. Instead of having a AND gate here, we would have an OR gate, and we would have this little NOT gate in front of it. So this would be the two inputs, and this would be the output here. So this thing is called a NOR gate, and this is the truth table here for our NOR gate. And this is the final gate we're going to look at here, and it's called an exclusive NOR gate, and this is the truth table for it here. So that's all we need to know about our gates. If you're quite inquisitive, you still might be sitting there scratching your head thinking, okay, we've still got all these gates and different types of gates, but how is it that whenever you stick these simple things together, you're able to create really vastly complicated things like CPUs that do amazing things and have hundreds of millions of these transistors that operate at billions of times a second? How is that possible? Well, we're going to find that out over the rest of the course. So thank you for listening. I hope this was a useful introduction if you haven't seen any electronics whatsoever. Now, even if you don't really understand all of that, it's not going to stop you from starting the course. Once you get started on the course, you'll get to use some of these gates and you'll get to build them in the Logisim, and you become used to seeing them. And you can always have a little look on the internet as well if you're interested in chase of any of those details. So thank you for listening. I'll get you on the next video. Goodbye.